Hi, my name is Daniel Chow, and I will be presenting my paper on robust GPS-based timing for phasor measurement units, a position information aided vector tracking approach. This paper was first presented at the ION GNSS Plus 2014 conference, and this work was completed together with Dr. Liang Heng and Professor Grace Gao. So first, a little bit about GPS. GPS, or the Global Positioning System, was developed by the Department of Defense during the early 1970s as a method of quickly locating military assets. The Global Positioning System operates by using a network of satellites with common clocks to quickly determine the position of a GPS receiver. In the process, it also calculates the absolute GPS time. The basic equation for calculating this GPS navigation solution is shown here on this slide. And if you have any questions about anything here or in the rest of my presentation, please come see me at the poster session afterwards. So now a little bit about PMUs, or phasor measurement units. PMUs are GPS-based devices that provide precise electrical wave measurements at a high sampling frequency. Currently, wave measurements using conventional measurement technologies, or SCADA, are sampled at one sample every 4 seconds. PMUs, on the other hand, can collect up to 60 measurements a second. Since each PMU's measurements are timestamped using clock measurements from the Global Positioning System, we can place phasor measurements from 2 different PMUs that may be separated by thousands of miles onto the same phasor diagram. These high-fidelity state measurements can then be used to further analyze and control the power system. So since the PMUs rely so heavily on the clock measurements from the Global Positioning System, we need to ensure that the GPS receivers used in these PMUs are reliable. Most commonly, the interference encountered by GPS receivers are non-malicious, such as high-powered radio signals leaking into the GPS frequency band, naturally occurring electromagnetic fields, or accidental jamming. We also have to consider the possibility of malicious attacks, which are known as spoofing attacks. Since we want to ensure that the GPS navigation solutions used in PMUs are reliable, our goals are to increase a receiver's robustness against interference, which would combat the frequency leakage, interfering EM fields, and accidental jamming, to be able to detect spoofing, and to improve the timing solutions generated by the receivers. So here's a brief outline of what I'll be going over for the remainder of the presentation. So first, our approach and implementation. To meet the goals set in our motivation slide, we proposed this position information aided vector tracking loop, also known as PIA vector tracking. The basic idea behind our proposed vector tracking algorithm is that we can leverage our knowledge of the true position of the GPS receivers used in these PMUs to better predict the code and carrier measurements used in tracking the signal. By leveraging our knowledge of this true position, we can significantly reduce the search space, the vector tracking loop search space, in the X, Y, and Z directions. We then use a Kalman filter to recursively predict and update our navigation errors, and we finally use a narrowband loop filter to further improve the tracking capabilities. So before I talk about our PIA vector tracking, this is the architecture for scalar tracking. This tracking loop is what is in most common GPS devices. It operates by tracking the Doppler frequency and phase shifts of a satellite GPS signal. In this block diagram, the channels correspond with visible satellites. So if you have 8 visible satellites, you'll have 8 channels. What's important to note here is that each channel operates completely independently of the others, which means that no information can be shared in between the channels. Now, here's the block diagram for the position information aided vector tracking loop. The blue blocks indicate the major components that have been added from starting from the scalar tracking. Now, I won't go over all the details, but the basic idea is that we take the navigation solutions that are estimated by the Kalman filter, correct them using our known true position, and use that to then calculate our Doppler and phase terms by creating line-of-sight projections between the receiver position and our projected satellite positions. By doing so, we then link all of the channels together through the same position information and time information, and this will improve the solutions generated by this tracking loop. So now our experimental results. So the hardware used in this experiment consisted of a receiver and antenna. The receiver, we used the TCIPG sampler, which is a low-cost, off-the-shelf receiver, and for the antenna, we used a Novatel fixed reference antenna. In the top figure, we have the TCIPG. It's the thumb drive-shaped object, and the Novatel antenna is the white cone-shaped object in the bottom. So after collecting the data, we then processed the GPS signals for both the scalar and the PIA vector tracking loops. For this data, there were 9 satellites in view, and the results are shown in this figure here. On the x-axis, we have time in seconds, and on the y-axis, we have clock error in nanoseconds. The red line is the results from the PIA vector tracking, and the blue line is the results from the scalar. From these results, we can clearly see that by leveraging our known true position, the PIA vector tracking loop was able to significantly reduce the clock errors when compared with traditional scalar tracking. So we wanted to determine how much better the position information aided vector tracking loop would perform when compared with scalar tracking. So we simulated 1 to 10 dB of noise and applied it to this GPS signal. We then processed the data for both the scalar and the PIA vector tracking, and the results, and I'll show you the results now. So up until we reached 4 dB of additional noise, both scalar and position information aided vector tracking worked fine. Now, however, at 4 dB of added noise, scalar tracking was only able to produce decodable navigation bits for 4 channels, whereas the original data could track all 9 of the channels. This shows that as you increase the noise, scalar tracking will give you worse and worse results, as is seen at from the figures at the bottom. Okay, so after we increased the noise past 4 dB, scalar tracking was unable to produce decodable navigation bits in 4 or more of the channels, which is the minimum you would need in order to produce navigation solutions. So, however, the position information aided vector tracking loop was still able to continue operating until we reached 9 dB of additional noise. This means that if a PMU receiver was running our proposed vector tracking algorithm, the jammer would have to get closer or output a stronger jamming signal in order to successfully jam our PMU receiver, both of which would increase the jammer's chances of detection. So we also wish to determine how our vector tracking algorithm would fare against a meakening attack. So meakening is where an attacker will record legitimate GPS signals and broadcast them elsewhere. Now, if a receiver running regular scalar tracking was to come under the attack of a meakening attack, their navigation solution would be identical to the navigation solution of the attacker. So here we've simulated a meakening attack, and as you can see, due to the fixed position nature of our vector tracking algorithm, the position information aided vector tracking loop failed to converge as soon as the meakening attack began. This shows that the failure of the position information aided vector tracking algorithm could be used as an indication of a possible meakening attack. So finally, the conclusions. So in this presentation, we proposed the position information aided vector tracking approach for robust GPS-based timing for phasor measurement units. We then conducted experiments to evaluate the performance of our vector tracking algorithm and found that the position information aided vector tracking loop was more robust against jamming compared with scalar, could successfully detect demeaning attacks, and also improve the timing solutions generated by the receivers. And again, if there are any questions, please come see me at the poster session.
Okay. All right, thanks very much.